Okay, so let's start. So most of the people has arrived. Let's begin. So today we are going to talk about BJT. Okay. So BJT is similar to diode in some sense, and I gave you task to you to simulate the bridge rectifier. Okay, only one of your friend asked you to install the software for in her laptop. Okay, so if anyone need help, I'm ready to help. She can also help you. Okay, then let's continue. Okay, so today we are going to talk about the BJT. So the circuit shown here is the Darlington pair. The name is given here. This is commonly known as a Darlington pair. Here we use a pair of BJT. Okay, so and here the task is to determine the quiescent condition, means we have to find the biasing point. Okay, or the Q point, biasing point or the Q point. This is our intention to find here a Q point. These two things we want to calculate. Okay, so this is putting in the node. Okay, so Q point we have to find. Okay, this is our target in this experiment. So before we start, our task is to look into the BJT. How we write a BJT in SPICE. Okay, so BJT, you know that BJT is like this. Okay, so this is NPN and this is say PNP. And let me change the color. Let me highlight the thing small. Okay, so this is N and this is PNP and this is NPN. So what is the base? This is base, this is collector, and this is emitter. And for this PNP, this is base, this is emitter, and this is collector. Okay. So for only the name is different, arrow is different, and the number of name of the nodes are same, although but the position is different. Okay. So we have CBE, collector base emitter. Here we had EBC, emitter base collector. So this is how we draw the BJT circuit. Okay, this is the circuit symbol of the BJT. Now the thing comes how we write, how we represent BJT in SPICE. Okay, so the symbol for BJT is Q. Okay, like for diode it is D, resistance it is R, inductor is it is L, capacitor it is C. Similarly for the BJT the symbol is Q. If there are more than one BJT, so we will write Q1, Q2, Q3, like that we will give the name. Okay. If we have multiple BJTs, but the symbol will remain always the same. Okay. The symbol is Q. Small q, capital Q doesn't matter, as I already told you that. And SPICE, the is case insensitive. Okay, it doesn't sense the case. Okay. So this about BJT symbol. Then how we write the terminals. Okay, so we always write terminals in this format: C, B, okay, independent of whether it is a NPN or PNP, whatever it is, we write it in this format always: CBE. Okay, so first we will write the collector terminal, then we write the base terminal, and then we write the emitter terminal. Okay, we will write in this format. Then after this we always give some name for model name. Okay, as we have already talked about the models. Okay, so we have to give some name. So here it is given QM. Let's say we give it name QN. Okay, so you can give some other name also. This name is material. You can give some number or name, whatever you want. You can give, no problem. Okay, so we have given the model name. Okay, so we have defined the BJT, Q, CBE, then some name of the model. Then we call the model as usual. Whenever we are using something different from the RLC, we have to give the model. Okay. So for diode we give in the model. So for BJT also we give the model. So we call it dot model. Then the model, which model for which BJT we are defining this model. So for this BJT we are defining model. So we have to give the name here for QM. Okay. So for QM, whatever we are defining here. Okay. Then so we have as I told you, this these two names must be same. Okay. These two names must be same. Okay, now here it comes that what type of BJT we are defining. So here we are talking about the NPN. So I will write NPN. Okay, NPN. Then in the bracket we define the model parameters. Okay, so if I give you the model parameters, so you will write the model parameters inside this bracket. Or the other possibility is same as we did in the previous case, that we can import a model from the model library. Okay, so we will see again. We will see the both the things here. How we can do the same things by writing the model and by importing the model. Okay, so I hope till now what I have introduced you is how BJP is defined. Okay, whether it is NPN or PNP, the format and the order of the nodes will be always be same as CBE, collector base emitter, and the name is always Q. And this model maybe is this is our choice name. Whatever we want to give, we can give the name, no problem. Here we can write BJT as well. Okay, whatever you want to write, you can write it, no problem. Okay, and then if the model BJT is NPN, so we write NPN and bracket parameter inside whatever it is. If it is PNP, so we write PNP here, PNP, and then the bracket and whatever the model parameters are there. So like this we define the BJT. Okay, I hope there is no doubt in or confusion. If you have any question right now, uh, so far you can ask. Okay, then we'll move ahead. So you learned how to write BJT. Okay, so let's move to the SPICE. Okay, so here already you can see that the numbering is already given. So this is the node 1 is defined. It is node 1. This node is 3. This node is 4, and say this node is 2. Okay, so 1, 2, 3, 4. All the nodes are defined here. Now we want to draw the circuit on the SPICE. Means we have to write. We want to write the circuit in the SPICE. So let's say let's go to the SPICE. So this is SPICE. So what we will do, first of all, we will say new file. We'll do the new file. Let's keep it here. Circuit you already know. We can switch always here and there. Okay, so what we are doing, first of all, first line is title line. So this is Darlington here. Okay, then let's define the signals. Okay, so I'll see here. So first is the input. Input is between 1 and 0. So this node is always 0. Okay, so input is Vn between 1 and 0, and the value is 5 volt. Okay, so you can see. So this we have finished one term, one DC supply. We have finished Vn 5 volt DC. Another is between here I named it 2. This is VCC is between 2 and 0, and the value is 12 volt. VCC is for supply we use, biasing we use. This is called the biasing voltage. So this is 2, this is 0, and the value is 12 volts. Okay, if I told you already, if I don't write volt, it also understand that it is the voltage. Okay, so I have written the two voltages was there. I have written the two voltages. Let's write the resistances. So one resistance is RB. RB is connected between 1 and 2. This node is 2. Okay, don't forget it. So this node is 2 and this node is 0. Let me write it again. Okay, so when we are writing about the RB. RB is connected between 1 and 2. So let's write it here. RB between 1 and 2. Okay, I forgot to see the value. So it is 47K. So RB is 47K. Next, the resistance is RE. It is 4.7K and it is connected between 4 and 0. So we go here. The resistance is RE between 4 and 0. The value is 4.7K. So this is all about the voltages and the resistances. Next comes the BJT. Okay. So let's define this Q1. So Q1 base is connected to 1, collector is connected to 2, emitter is connected to 3. So we'll write CBE. So collector is 2, base is 1, emitter is 3. So we'll write CBE. So we'll write Q1, C is 2, B is 1, E is 3, and the name is QN. Okay, you can give some other name also, no problem for that. Okay. Then we have another BJT, and let's see what are the nodes. Okay, so this is Q2. Q2, the collector is 2, base is 3, and the emitter is 4. So this is 2, 3, 4. 2, 3, 4. And the name, we are using the same model for both of them, so we can give the same name. Okay, we are using different models. Suppose if I want to give different model, different parameters for each BJT, here we are saying both the BJT are same. Okay, so both the BJT are same means the model will be same. If we want two BJTs to be different, we can keep their model to be different. Then those BJT will become different. Okay, so dot model, we will call the model, and for which name? For QN. So both these are NPN. NPN. I'm not writing any model. Okay, it will take some default model by itself. Dot model, it is finished. Okay, so this is finished. Okay, in the description of BAT, if there is any doubt, any problem, you can ask. In the description, name, model, I have written here in the circuit. If you have any doubt in this regard, can ask. Okay, so it is not there. Okay, so we have defined the circuit completely. Everything is done. Now the important thing is what we want to do with the circuit. Okay, so the thing is that we want to calculate the uh, quiescent point. Okay, we want to calculate the quiescent point, the biasing point. So the biasing point is calculated by using the dot TF. It will give us the transfer function dot TF dot TF. Okay, this dot TF gives us the transfer function. Okay? Gain of the circuit. Okay, so here we want the output. Here it is biasing. So we want to take the yes. So we want to what we have done is we have written all these things. The model is here. We want to use. We want to write. We can write this model as well. So first of all, we want to calculate the transfers analysis. Okay, so we can do the AC analysis also. We'll do it after some time as well. Okay, so what is this V4? Okay, so we want to check the transfer analysis. Like this point is V4 and V1. So how the input transfer to the output is decided by it. I'll explain you what is the theory behind it. Okay. So dot TF V4 and V1. Okay, and because V is when we are applying input dot N. Okay. So I'll explain this step even in more detail. So what this .tf means, like see, you can see that in this whole function, there is, I didn't define what we are doing, AC, DC and transient, we have not defined anywhere, okay, because we are not calculating the response of signal, like DC we are applying, we are seeing output. What we are seeing that we have applied some DC input signal, a biasing signal, only these two we have applied, okay, and this DC is constant 5 volt. So if we keep it constant, all voltages are constant. If we keep all voltages as constant, so this is 5 volt constant. If we keep this as constant, so what will happen? It will give a constant voltage at all points because everything is constant, everything is DC. So it will give a constant voltage here, it will give a constant voltage here because this DC is also not changing. This DC is constant. This is also constant. So once it will do the calculation and give a constant value. So here we'll get 1 point, here we'll get another value. Okay. But what it does when we do the transfer analysis, .tf function, okay, .tf function we can also name it as the v in here, okay. So .tf function, what we say, we write .tf output and input, output .tf space output space input. So output we are taking at 4 and the input we are taking at input is at vn, okay. So there is some error from the typing here. It is 2, actually it is 4. Okay, so here we are taking the output. So what it does, like DC. If we are at DC means we are at fixed point. Okay. So if we take the x-axis, y-axis. Okay. So the output voltage here will be fixed. The input voltage is fixed. Input voltage is at 5 volt fixed. Okay. So corresponding what will be the output, it will be displayed here. But what it does, it gives a minus AC disturbance to this. Okay, some disturbance will be here and this disturbance will cause the output to change. Okay, so at this fixed point, this .tf function gives a smaller perturbation. Okay, so there will be minor disturbance or signal variation, and because of that variation the output signal will change. Okay, and this is reflected, and this, by this we can calculate the input resistance of the device. Means if we apply input here, what will be the resistance seen by this? If we what we are getting output here, what is the resistance seen by this output node, and also the gain of the circuit. Okay, and this calculates the DC gain of the circuit. So these things we came to know by using this .tf. Okay, and in .tf you can see that we have not applied any .dc, .ac, .transfer, nothing we have applied. Okay, so this is the definition and the theory behind this .tf. Okay, so let's go back to the SPICE. Okay, so let's see if I run it like this, will it run or okay. So I have to save this, so I save this. So .cir, so let's say Darlington, this for here, .cir, okay, Darlington for here, okay. So now I'll open it, open .circuit file, Darlington, well, yeah, it is Darlington here. Okay, now you simulate. So you see that here it says the extra text online. Because here what it expects, it doesn't, I have written here V1. Okay, it should have the same thing what we are writing here, that is the input voltage. So whatever we have written here, we should write it here. So if I write it, so it will be correct now, and it should give the answer. Okay, so now you see that there we are not getting any black window because we didn't apply dot probe. Okay, and dot probe was not required because in this case, whenever we apply the dot tf, our intention is to calculate the input resistance, the output resistance, and the gain of the DC gain of the circuit. Okay, so the input resistance and output resistance are very important things of any amplifier, okay, or for any circuit. Okay, So they cause many changes in the circuit. So they are very important to know about the input resistance value and the output resistance of any circuit. So for this circuit, what is the input resistance? Okay. So as you can see the simulation is complete, but we didn't get any output or the black window, because we will not get the black window because we didn't apply the dot probe command. Okay, so where is the output? So go to the view and check the output file. Okay, so this is our circuit. This is our circuit, BJT model parameters, small signal bias solution. You see that this came small signal bias solution. Okay, so as I told you that there will be a small disturbance, a small perturbation in the circuit, and according to that it calculates the bias variation. Sorry, the that input output resistances and the gain. So V in is okay. So these are the minor differences that current flows in the V in. So the V in current flows is this much. Okay, it is like 1.4 or 0.1489 milliampere. This is negative just to show the direction. So how much power is dissipated, that we also know. Okay, in this calculation, it is 10.2 milliwatt power is dissipated. Now the important thing that we were looking for is the small signal characteristics. So small signal characteristics tells us the gain. Okay, so this is V4 over Vn, means output over input. What is the gain of the circuit? The DC gain. So the DC gain is 9.85. It is almost, you can see it is like nearby 1. Okay, so if I write it more precisely, so it is like 0.9858. So it is nearby 1. Okay, so the gain DC gain of the circuit is nearby 1. This is the input resistance. You can see this is the input resistance is 4.65. It is like 47, approximately 47 kilo to 47 kilo. So it means that okay, and what is the output resistance? It is like 66 ohm only. Okay, 66 ohm. Okay, so this is like 66 ohm, and this is like 40 ohm. It is, let me write it there, ohm. And here it is 47 approximately kilo ohm. So you can see that how it came. So it means that when we apply any input here, it will see the input resistance as 47 kilo ohm. But the output resistance that is visible here is, although it is 4.7 is connected here, but when we see the output resistance here, or we connect something here, okay, so when we see it is here, so what we will see, the resistance is 66 ohm only. So the output resistance is small and the input resistance is large. Okay, so if we use any amplifier, so for any amplifier, the required characteristics is voltage amplifier I'm talking about. So whenever we use a voltage amplifier and we want a voltage amplifier, so what is the required characteristic? Input resistance must be high and the output resistance must be low. So we can use this circuit as a amplifier because input resistance is high and the output resistance is low. But the problem with this is that the gain is nearly 1. So gain of the amplifier is approximately 1. Okay, so amplification is not an advantage in this case because the gain is not greater than 1. It's rather less than 1 also, but it is nearby 1. Okay, and the input resistance is high and the output resistance is low. Okay, so we can use it as the buffer. Okay, buffers, the buffers are the circuit that we use for the impedance transfer. Means like this, we connect input like this. This is input and this is input. This is output. This is output. This is input. So input side impedance will be different and the output side impedance will be different. So here it is 47K, here it is 66K, and the gain is 1. So input and output will not change in value much, but their impedance will be changed. Okay, so this is used sometimes for the impedance transfer to remove the loading effect. Okay, so some other time I will explain the loading effect also. So but right now it is good. Okay, so to remove this loading effect, we need to change these things. Okay, in this whole exercise, if you found any if you feel any difficulty, you can ask. You are free to ask. I am here. Okay. I'm waiting for
सर
you. Yes.
सर दोबारा से एक्सप्लेन कर दीजिए रेजिस्टेंस वाला कि 67 और 47 कैसे आया था?
अच्छा देखिए 67 और 47 कैसे आया ये हमारे लिए मीन्स हम ये बात को नहीं ये तो इसने अपनी खुद ही कैलकुलेशन की है ठीक है मैं बस आपको ये बता रहा हूँ कि हमें अब यहाँ से देखेंगे मीन्स हम जब इसके अलावा हम डीसी के साथ सपोज यहाँ कोई सिग्नल और लगाते हैं ठीक है तो क्या होगा कि उसको रेजिस्टेंस यहाँ से कितना रेजिस्टेंस दिखाई देगा उसे लगेगा 47 किलो ओम का रेजिस्टेंस हमें यहाँ से मिल रहा है सामने से और जब हम आउटपुट यहाँ पर लेंगे ठीक है आउटपुट को हम लेकर के सपोज यहाँ पर कहीं कनेक्ट करेंगे ठीक है तो अगर हम और आगे सर्किट कनेक्ट करते हैं तो यहाँ से हम जब देखेंगे तो हमें कितना रेजिस्टेंस दिखाई देगा 66 ओम का रेजिस्टेंस दिखाई देगा ठीक है क्योंकि हम कई बार क्या होता है एक सर्किट का आउटपुट दूसरे का तीसरे में ऐसे कनेक्ट करते हैं तो हम इसका इफेक्ट देखेंगे तो हमें यहाँ से हमें कितना आउटपुट रेजिस्टेंस दिखाई देगा 66 ओम रेजिस्टेंस आउटपुट हमें दिखाई देगा आउटपुट रेजिस्टेंस दिखाई देगा और गेन गेन तो आपने देख लिया गेन क्या है स्मॉल सिग्नल गेन हमारा नियर बाई 1 है तो इस सर्किट को एज अ एम्पलीफायर यूज करने से कोई फायदा नहीं है क्योंकि गेन हमें नहीं मिल रहा है हाँ एम्पलीफायर की कैरेक्टरिस्टिक्स जो है कि 47K और इनपुट रेजिस्टेंस लार्ज इनपुट रेजिस्टेंस एंड लो आउटपुट रेजिस्टेंस ये दोनों चीजें जरूर हमें इससे मिल रही हैं तो हम इसको एज एन एम्पलीफायर नहीं यूज करेंगे हाँ एज अ बफर हम यूज कर सकते हैं ऐसे बफर का मैंने आपको बताया कि सिर्फ इनपुट आउटपुट का रेजिस्टेंस चेंज करने के काम आते हैं सर्किट्स इम्पीडेंस ट्रांसफर भी बोलते हैं उसको ठीक है so what we where we have seen so here is that output yeah so you can see that this is the V4 over Vin the gain is like 0.98858 it's almost 1 and the input resistance is large and the output resistance is low and here it is written job okay so this is another different from the normal league we have seen AC, DC and transient analysis but here it is different okay so we have kept the dot tf and dot tf gives us what this okay if you ask in the question that calculate the input resistance and output resistance and the dc gain so automatically you should think that you have to apply the dot tf command okay and remember this deliberately I did not write v in the initially I write v1 so that you understand that here whatever the name of the input we have to write the name of the input here okay and for the output we have to write the node v4 v at 4 node we are taking we write the node okay so deliberately in the beginning I wrote here v1 okay so you remember this thing I hope this is clear to all of you okay so since it is an amplifier we can apply some AC signal as well so let's see to applying AC signal okay okay yes before that before that before that what is left that I did not give any you can see that I did not give any values of the NPN transistor okay so when I write like this NPN and bracket I leave it means that the software will automatically take the default values default parameters and it will simulate it okay so this is the case now if I want to give the parameters so let's say these are the parameters that we want to give let me copy it it is not copied so bf is 100 br is 1 rb is 5 so let me write it so just to show you bf is 100 br is 1 or 5 how much it was br is 1 yeah rb is 5 rc is 1 rb 5 rc 1 re 0 rb is 5 rc is 1 RE is 0. Okay, these all are actually the small parameters of BJT. Okay, and BJE, it was defining some BJE. Let's see what is that. Where is that one? BJE is zero point 0.8 and BA is 100. 0.8 and BA is 100. Capital is small doesn't matter because we are using a default parameter. Let's run it now. See if changes. So again it is completed. Okay. So I've written the now model output file. Let me show. Again we are seeing the output file, and you can see that there is not much difference. Although there is a 4th place difference here, and the value here is also a little bit different. Here almost same, not much difference is there. Okay. So okay, so these are like this. We are given the model. We can write that model. If we are not given the model, we can use the default model. Okay, if it says that, if the question says use the default model, so you just need not to write any parameter, just do it. Okay, so it is done when you are writing default parameters. Otherwise, if your model you are given, you have to write the model here. The third possibility is that you are asked to use a particular model from the model library. So if it is case, then we have to go to the model library. So we'll go to the model library and I will open the model editor. Model editor. So this came the model editor. Open this. So what we want to see, BJT we want to see. So let's say BJT I click. So BJT directly not came. So let's say like bipolar. Bipolar dot lib. So many models of the BJTs are there. Okay. So you can see so many models of the BJT are there. Okay. Question may ask you to use particular model, give the name, and you have to use that model. Or if it is not asked, you can leave by default, or like number is given, then you have to use, let's say, what is this model? This is NPN model. Okay, good. Okay. So let's use this model. Let's see what is the effect. So let me copy this. I can copy whole as well. No problem. Okay. So so I paste this dot model here. So you see that all so many parameters are there. So but one thing I have to keep it same. So need to keep this name as same as this. Okay. So I use this copy and I keep it here. Paste again. Paste. This is paste, and now I simulate and let's check. Again we got the answer. Okay, simulation complete. It shows the here it is simulation complete. Let's see what is the output. So the output says what? So you can see that there is not much difference in the values. You can see that this is also increased to reduced to output will reduced to 60. Okay, and the input resistance is almost the same as it was. Okay, and the gain is almost again the same thing. So if the model is given, so I have shown you the three ways how we can write a BJT model. We can import the model from the library. We can write the model. Question may give you the model itself. You have to write those parameters. If the model is not given or the model number is given, then we have to go to the model library. If I ask you to use this Q2N718, so you will open it and copy this and paste it there and change the name. Don't forget to change the name. Okay, this is very important. Okay, so if you keep this name and this same. Okay, don't forget it. So I hope now you can use this spice in this case. Okay, so this is one of the portion of the BJT that we can. This is one of the circuit of the BJT that we can use. Okay, so meeting is going to stop in 5 minutes. So rather I'll stop it by myself and it'll start in 5 minutes. Okay, not in 5 minutes means I'll start. Okay, is there any question? Is there any problem right now? Any question, any problem right now? We can see it. Okay. So this is a simple circuit. We have seen only the transfer function, and we have also introduced the BJT. Okay, so we can write the two BJTs as well. So soon we are going to see the uh, NPN amplifier. Okay, or common emitter amplifier. This is one of the very good amplifiers that we use in circuits. Okay, so if you don't have any doubt, any question, so we can continue. Okay, so you stay there. Okay, rather let it get stop automatically. Then okay, so we are going to see the next circuit. Is the where is that circuit? Using it to you. Yes, yes, yes. Okay. So what we are going to see now, this is the circuit, and this is called the common emitter amplifier. Okay. Common emitter amplifier, common emitter configuration. Okay, so BJT has three type of configuration: common emitter, common base, common collector. Okay, whenever we use BJT, so we prefer to use the common emitter configuration, because in that case, this works as a amplifier. Okay, so we get good gain. Input impedance is good. Output impedance is low. Input impedance is moderately high. So like that, we get the functions here. Okay, so don't worry about so many components. Okay, I'll explain their working and meanings and importance. So don't worry for that. Okay, so the first thing that you should notice is that the number of BJT is given. Model number is given here. Okay, it is Q2N2907. So the model number is already given in the circuit. Okay, so this is one thing different. Okay. Another thing is, what type of BJT is this? Is this NPN or PNP? This
PN.
is yes, yes. This is PNP. Okay. So we can make the common emitter amplifier by using the BJT NPN as well. Okay. So we can do that thing as well. That is not a problem. Okay. मैं आपको बता दूं. If you just change this, make it emitter, make this as a collector and this emitter. Okay, and if you reverse this polarity, it will work as the NPN. Okay, not much difference will be there. I'll show you that also. Okay, so what is simulate and study transient and frequency response? So we have to see both things: transient and frequency response of BJT amplifier and common emitter configuration using PSPICE windows. Okay, so it may be about to end. This meeting may be about to end. So as soon as it finishes, I'll restart it, and then we'll continue. Okay, so don't go anywhere, because we'll continue from here. Okay, so as I'm telling you that we can revert it back. Okay, तो अगर हम इसको यहाँ पॉजिटिव कनेक्ट कर दें, यहाँ नेगेटिव कर दें, तो और इसको हम रिवर्स कर दें, so क्या हो जाए 15, ये रिवर्स कर दें, इस एरो को ऐसा हम कर दें, तो ये एनपीएन हो जाएगा, और आप देखेंगे तो ये सेम फंक्शन आपको कॉमन एमीटर एनपीएन बेस्ड एम्पलीफायर की आपको फंक्शन दे देगा. So सो यहाँ पर कुछ कैपेसिटर्स लगे हुए हैं, तीन कैपेसिटर लगे हुए हैं, इनके नाम होते हैं. इसको C1 को बोलते हैं कपलिंग कैपेसिटर, C2 को भी बोलते हैं कपलिंग कैपेसिटर, और C को हम बोलते हैं बाईपास कैपेसिटर. ये इनके रीजन, इनके नाम के कि इनको कपलिंग कपलिंग क्यों बोलते हैं, और ये बाईपास कैपेसिटर क्या है. ठीक है, और ये तीन इंपॉर्टेंट कैपेसिटर्स हैं. ठीक है, ये रेजिस्टेंसेस यहाँ पर लगे हुए हैं. इस रेजिस्टेंस को हम R2 बोल रहे हैं, इसको R1 बोल रहे हैं. ये RS है, ये सोर्स का रेजिस्टेंस होता